sigma PL. Right. Now if you plot some kind of a graph wherein I represent lambda on the x-axis and I represent sigma CR on the y-axis, so to solely this relation, what we'll have is some kind of a form like this, right? Because lambda and sigma are inversely proportional and lambda is to the power of 2, so basically it will be some kind of parabolic shape, so it will be like a curve like this basically. Now let us assume that this is my value of sigma PL, right? This is the value of sigma PL, and the corresponding value, lambda value at sigma PL is essentially suppose lambda 1, right? And this is suppose lambda 2. So at values of lambda from lambda 1 to lambda 2, what we have is some kind of a slenderness ratio wherein column design will be governed by stability criteria. Because here what happens is that we cannot use the strength criteria because for example, let us say this slenderness ratio, this is for example a sample slenderness ratio, and the value of the Euler critical load or the Euler compressive stress at this slenderness ratio is suppose sigma S. Now at this point sigma S is obviously sigma P is less than sigma PL. So if I design the column using sigma PL, which we essentially do, that is from the strength criteria, what we essentially neglecting is buckling, because the column is expected to fail by buckling because sigma S is less than sigma PL, right? So, or I should say this is also my critical CRS, critical of a sample, right? So as this is less than sigma PL, essentially this will fail by buckling. So till this point from A to B, what we do is that the column criteria, the column design criteria I should say, is governed by the stability limit, that is all these regions. Now above A, what happens is that this relation is not that valid, because this relation is valid till sigma CR is less than sigma PL, right? And sigma PL is here, so above this relation doesn't hold true. So the other extreme, at very low values of lambda, what we have basically is that a very high value of this sigma CR. At very low values of lambda, we have a very high value of sigma CR, and therein what happens is that sigma CR has already exceeded the sigma PL. So here we cannot utilize the buckling as the governing criteria. So we got to utilize strength here as the governing criteria. And suppose that if this is sigma PL, suppose this is sigma max, and the working load is based on this ultimate load, ultimate stress I should say, right, for limit design. Now what we have is that if strength is the determining factor, then for short column, for example till this value of lambda, that is, let's say this is sigma I should say sigma 3, from 0 to sigma 3, from 0 to lambda 3, what we have is that the design for small columns, right? And this is governed by solely strength criteria, right? Now between lambda 3 and lambda 1, the slenderness ratio are not small enough. The slenderness ratio are not small enough to fail to be only governed by the strength criteria, but also are not big enough to be governed by stability criteria. What we have is basically the amalgamation of this and this basically, and that we can do by plotting, by joining these 2 points like this, right? For example, A to C we can join, and this is suppose C to D, right? So the graph is BACD, wherein BA defines the stability criteria, and this is for long columns. AC defines the critical, the stress I should say for the medium sort of columns from lambda 3 to lambda 1, and CD defines the design criteria, that is only basically the strength criteria for very short columns. So a brief synopsis of this is, if we have a very lower value of lambda, that is the slenderness ratio basically, then column design is only governed by strength criteria, and that thing we utilize in case of short columns, right? If you have very high values of lambda, what basically happens is that the I should say, the Euler's critical stress, right, takes into prominence, and column design is governed by stability criteria. So this is what we have for long columns. In between, there are some slenderness ratio whose values are not small enough to fail by strength criteria, but are not big enough also to fail by stability criteria, right? So what we do is that we amalgamate the two and we have some kind of a stress in between, right? So this is the whole structure of the design of columns. Whether the column design should be governed by strength or stability is determined by the lambda or the slenderness ratio, right? And the slenderness ratio, and I should say the Euler's formula is valid for all values of lambda, wherein the sigma CR is lesser than the stress at the proportional limit. And that is all for this lecture. Thanks a lot for listening. Thank you.